Let's get started. This theorem from Fermat states that any odd prime p can only be expressed as the sum of two squares, where p equals x squared plus y squared, if and only if p is equivalent to 1 mod 4. Now, just a quick note, IFF, if with two f's, means if and only if, and these three lines here mean congruent to, and we use that for modular arithmetic. Now let's work some of this out to see what pattern it shows. These are the first few primes from 1 through 100, and they're all odd. Now, you've probably noticed that odd primes is just any prime that doesn't include 2. Let's see what these equal mod 4. 3 is equal to 3. This is 1, 3, 3, 1, 1, 3, 3, 1, 3, 1, 1, 3, 3, 1, 3, 1, 3, 3, 1, 3, 3, 1, 1. Now what does this pattern show us? Right now it's pretty hard to tell, but we can see later on that these numbers will have something in common. Now let's get on to the proof. I'm going to call this a mini proof because there are two parts to it and we're only going to prove the second part. But by proving the second part, we do show the correct basic idea. The first part of this proof states that for any odd prime, -1 is a square mod p, if and only if p is equivalent to 1 mod 4. The second part of this proof states that for p, odd obviously, p factors into the product of Gaussian integers only if p is equivalent to 1 mod 4. Just a quick note, Gaussian integers are numbers that can be written as a plus bi, where a and b are integers. Some examples of Gaussian integers are 1 plus 2i, 4 plus 6i, 3i, 17, 27 plus 14i, and a lot of others that you can probably think of. Now let's assume that 1 is known. Then, using 1, we can show, through the definition of a square in mod p, that x squared is equivalent to -1 mod p. Then, we can rewrite that as x squared plus 1 divides p. Since x squared plus 1 divides p, and you can rewrite x squared plus 1 as x plus I times x minus I, that means that p is the product of Gaussian integers. Let's see if this matches up with what we found before. These are the first few numbers that worked for 1 mod 4 and being an odd prime. Can we rewrite these as the product of Gaussian integers? The answer is yes. 5 is equivalent to 2 plus I times 2 minus I. 13 is equivalent to 3 plus 2i times 3 minus 2i. 17 is 4 plus I times 4 minus I. 29 is 5 plus 2i times 5 minus 2i, and so on. But, more importantly, we can rewrite these as the sum of two squares. 5 is equivalent to 2 squared plus 1 squared, 13 is 3 squared plus 2 squared, 17 is 4 squared plus 1 squared, 29 is 5 squared plus 2 squared, and so on. Yay! It works! Now for some practice problems. Pause here to work it out before I talk about the answers. Okay, I'll assume you've worked it out by now. Let's start talking about these. Can 299 be written as a sum of two squares? The answer is no. 299 is not prime. It's actually the product of 13 and 23. Can 8,647 be written as a sum of two squares? No. 8,647, while it is prime, is not 1 mod 4, so it wouldn't fit with what we just proved. It's actually 3 mod 4. Can 937 be written as a sum of two squares? The answer is yes. It's 1 mod 4, so it works with our theorem, and it's 24 squared plus 19 squared. Can 367 be written as a sum of two squares? The answer is no. It's 3 mod 4, not 1 mod 4. 181 can be written as the sum of two squares as 10 squared plus 9 squared. 20,000 20,753 can also be written as the sum of two squares, because it is prime and 1 mod 4. 20,753 is equivalent to 127 squared plus 58 squared. Well, that's it. And subscribe and follow on both Instagram and Facebook for updates and announcements.